Google's Sycamore quantum chip was once hailed as the breakthrough that would redefine the boundaries of science and technology. In 2019, Sycamore reportedly performed a calculation in 200 seconds that would take the most powerful classical supercomputer over 10,000 years to complete. The world watched in awe. For a brief moment, it seemed humanity had taken its first true step into the quantum age, a domain where the classical rules of physics begin to blur and computation touches the very fabric of the universe. The achievement was called quantum supremacy, a term meant to signal that quantum computers had reached a level where they could outperform even the best classical machines at certain tasks. But just 4 years later, IBM came forward with a claim that sent shockwaves through the tech world. According to IBM, the problem solved by Sycamore wasn't actually beyond the reach of classical machines. In fact, IBM engineers argued they could perform the same task in just 2.5 days using a conventional system, significantly undermining Google's claims. Suddenly, the narrative of quantum supremacy was thrown into question. Had we been too quick to declare the dawn of a new era? Or were we witnessing the messy, competitive nature of technological evolution, where each step forward is immediately met with scrutiny? The heart of this debate lies not just in raw computational power but in what we define as meaningful progress. Quantum supremacy, while a catchy phrase, may not be the milestone we hoped for. Some experts argue that the focus should be on quantum advantage, the point at which quantum computers can solve real-world problems better, faster, or more efficiently than any classical computer. And while we may not be there yet, the journey is undeniably underway. Quantum computers operate on principles that defy everyday intuition. While classical computers use bits, zeros and ones, quantum computers use qubits, which can exist in a superposition of both states at once. They can also become entangled, meaning the state of one qubit is directly connected to the state of another, no matter how far apart they are. This allows quantum systems to process a vast number of possibilities simultaneously, opening the door to solving problems that would be practically impossible for even the most powerful supercomputers. But harnessing this power is far from easy. Quantum systems are notoriously fragile. A qubit's quantum state can be disturbed by the slightest environmental interference, temperature changes, electromagnetic waves, or even cosmic rays. This makes building and maintaining a stable quantum computer an immense engineering challenge. That's why much of the progress in this field involves not just the qubits themselves, but also the materials, cooling systems, error-correcting codes, and architectures required to keep them stable. Despite the challenges, the race is intensifying. Companies like Google, IBM, Intel, Microsoft, and startups like Rigetti and IonQ are pouring resources into quantum research. Each has a different approach: superconducting circuits, trapped ions, topological qubits, and more. Governments are also heavily invested. The United States, China, and the European Union are all funding national quantum initiatives, recognizing that quantum technology could have massive implications for national security, economics, and scientific dominance. So what exactly could quantum computers do that today's machines can't? One of the most cited examples is in the field of cryptography. Many encryption systems today rely on the fact that it takes classical computers an impractical amount of time to factor large numbers into primes. But a quantum computer running Shor's algorithm could, in theory, break these codes quickly, posing a significant threat to digital security. This has led to the rise of post-quantum cryptography, an effort to develop encryption methods that would remain secure even in a world with powerful quantum computers. Beyond cryptography, quantum systems could revolutionize material science. Imagine being able to model molecular structures so precisely that we could discover new drugs in days rather than decades. Or simulate exotic materials and chemical reactions that would be too dangerous, expensive, or complex to study in real life. In finance, logistics, climate modeling, and machine learning, the potential applications are staggering. But not everyone is convinced. Critics argue that much of the hype surrounding quantum computing is just that, hype. Many current quantum machines, they say, are noisy and unreliable, suitable only for highly specialized tasks that don't have much real-world utility. There's also concern that we may be headed for a quantum winter, a period of disillusionment when expectations outpace results. The field has seen this before. In the early 2000s, quantum computing was largely relegated to theoretical physics departments. It wasn't until the 2010s, with new hardware developments and tech company interest, that it surged back into public and commercial awareness. Still, history has shown us that transformative technologies often take decades to mature. Consider the early days of classical computing. In the 1940s, machines like ENIAC filled entire rooms and could perform just a few thousand calculations per second. Today, your smartphone is millions of times more powerful. It's not hard to imagine a similar trajectory for quantum devices, if the fundamental challenges can be overcome. There are already signs that the field is maturing. Error correction, once seen as one of the biggest roadblocks, has seen notable advancements. Techniques like surface codes and cat qubits aim to detect and correct errors in quantum states, allowing for more reliable computations. Quantum algorithms are becoming more sophisticated, and researchers are finding ways to run useful calculations even on today's limited hardware through techniques like hybrid computing, which blends classical and quantum methods. Another promising area is quantum networking. Just as classical computers became vastly more powerful with the advent of the Internet, quantum devices may achieve new capabilities when linked together in a quantum Internet. This would allow for the transmission of entangled states across long distances, enabling secure communication channels and distributed quantum processing. Experiments in quantum teleportation and long-distance entanglement have already shown this is more than science fiction, it's a real, emerging field. And then there's the philosophical aspect of quantum computing, the idea that we're tapping into the deepest rules of reality. Quantum mechanics, with its probabilistic nature and strange phenomena, has always seemed like a riddle. By building machines that function on these principles, we are not only building tools but also conducting experiments into the fundamental structure of existence. Each new advancement is a window into a realm that challenges our assumptions about cause, effect, and information itself. So where does this leave us? With excitement, uncertainty, and a sense of cautious optimism. The path ahead will not be linear. There will be setbacks, competing visions, and shifting definitions of success. But the goal remains: to unlock a new layer of computational power that could forever change how we understand and interact with the universe. Here at Discovery at 2.0, we continue to explore the frontiers of science not because the answers are simple, but because the questions are so profound. The story of quantum computing is still being written. Whether it becomes the engine of a new technological revolution or remains a brilliant but limited tool depends on how we navigate the coming years. One thing is certain: this is a journey worth taking.